Hello everyone and welcome to DIPY Workshop 2021. My name is Serge Coudreau and I'm one of the core developers of DIPY. I'm also the release manager of the project. This is the second part of the image registration session. If you have not seen the first part, I recommend you to start with it. In this part, I will focus on methodology and affine registration. So, what are the components of the image registration algorithm? The image registration algorithm are composed with the algorithm, of course, the type of algorithm, of course, so that we can choose between streamline algorithm, image algorithm, and so on. We need the image pyramid, the mask, transformation, the interpolator, the matrix, the optimizer, and the sampler. I will go through all these components during this presentation. I will not go through the streamline algorithm since it is covered by Eleftherios Kefalidis on Wednesday. Let's go through the methodology of image registration. Of course, we start with a reference imaging and a floating image that is our moving images. The first step is to apply a transformation on this floating imaging. This transformation can be linear or non-linear. We'll talk about specific in the talk, the linear one. After applying this linear transformation, we need to interpolate the data. This data interpolation will permit us to switch from the moving grid to the reference grid. Now that our two images are on the same space, we can evaluate the two images, the similarity between the two images. Do they match? If yes, our registration is done. If they are not matching, we estimate again the parameters and we restart the loop. This iteration between this loop is done by the optimizer, as we can see here. Let's talk about more in detail about this block, the transformation, the nonlinear transformation block. So for the affine registration, we have many different simple transformation that we can apply on it, which is translation, rotation, rigid, similarity, affine, and so on. You can easily combine two different transformations with their own feature. So as you can see here, the translation preserves the orientation, the rotation on the rigid preserves the lines, the similarity preserve angles, and affine preserve parallelisms. So the similarity here is composed by the rigid transformation and the scale transformation, which is not present in this slide. The scale transformation is composed by one parameter. This is what we call an isoscale because we scale in the same factor on each direction, x, y, z in 3D. If we were not scaling in the same direction on x, y, and z, the similarity would be 9 degrees of freedom instead of 7. So after looking at after obtaining the number of degrees of freedom for each of our transformation, we can look more in detail in this slide what parameter will need to be estimated by our similarity metric. So in this case, for our translation, we can see that two parameters need to be estimated by our similarity metric. So you can see the difference with the previous slide that the translation was 3 parameters and now only 2 parameters. Why 2 parameters? Because we are in a 2D case here. We are estimating Tx, and Ty. In the 3D case, we need to estimate also the Tz. This is why we need 2 degrees of freedom. Same case for the affine. Here you can see that we need to estimate the translation and the rotation. So we have only 6 parameters to estimate, which in the 3D case, we increase the complexity and we have 12 parameters to estimate. After applying a transformation to our moving image, we need to do an interpolation of this data. As I said before, you can see here that we are in a grid of our moving images. The goal is to switch from a specific grid to the static grid and see what are the gray value in this specific grid. So this interpolation can be linear, trilinear, spline, or the nearest neighborhood. All the different kinds of interpolation are available on DIPY already, and you can play with it. You will have to pick your interpolation following your application. The next component that we will talk about are image pyramid and sampler. So for these 2 components, the main goal of these 2 components are to reduce the registration time, runtime. Indeed, registration is a really exhaustive and long processing. And if we don't want to spend day on day, we need some strategy to reduce the time. One of the first strategies is a sampler strategy that you can see here. Because you don't need all the information of your data, you might want to decide if you want to use a partial of it, or the whole data, or the sparse, or the sparse of it. So this information can be defined on DIPY on each DIPY function. Unfortunately, we don't have yet the sparse sampling, but the full and the dense sampling are and the partial sampling are available right now. Also, you need to use the image pyramid to avoid to be stuck in a local minima. So if you are doing your image registration in the world images, you can see that on some pixel, you can have a local minima where your optimizer will be stuck. So to avoid to have to register small detail of your images, the idea here is to smooth and subsample your data. So here you can see in this image, we have 4 levels of subsample. So we subsample, smooth, subsample, smooth, subsample, smooth. The fact is in this level 4, we arrive to a really small image with no detail, which permits us to register really the most basic element of our image. We go to the next level and we start with the previous parameter estimated on the level 4, and we try to register with a little bit more details. We do that minute 4 times here. This is where we can get the whole registration. So all of this permit to have a really smoother convergence to our ideal optimum. The next component that we will talk about is similarity matrix. So there is different type of similarity matrix. There is a feature-based similarity matrix, the intensity-based similarity matrix, and the mutual information-based similarity matrix. In DIPY, we don't have a feature-based similarity matrix. This is something that we plan to implement in the future. So I will not get into detail of this type of similarity matrix. Of course, as you can see in these pictures, you will have to choose a different feature of your picture to symbolize how similar they are. Here you can see that they pick specific point or specific region to mark as a similarity measure. Most of the time you will need a segmentation process or an extra step to compute these particular features. Concerning the intensity-based similarity matrix, you will find this most common function that you can see everywhere. So here we have the normalized cross correlation, the sum square difference, and the sum absolute difference, and of course the mutual information. The advantage of these metrics is they are perfect for monomodal data. So if you are in the same space, MRI to MRI, cities to city, pet to pet, they are really ideal. So the normalized cross correlation expresses the linear relationship between voxel and intensity between two volumes. As you can see here on this slide, when you apply this kind of computation, you can easily see a structure or a linear relationship of your data. So more they are dense, as you can see, more they are correlated. The advantage of this similarity matrix is they are super fast to compute. But everything that are super fast have a different cost. Here, the possible limitation that you could encounter is the sensitivity to noise or the sensitivity to pixel intensity, especially for the SSD and the SAD. Concerning the information theory-based similarity matrix, they try to describe how to quantify the quality of your alignment. So the joint entropy describes the amount of information described in your data. So all these metrics are quite advanced, and they work perfectly with multimodal data. The next module that will link everything together is the optimization method. It exists a different scheme of optimization method. There is the gradient-based optimization one and the gradient-free optimization one. In this kind of problem, we are used to use the gradient-based optimization. You have to know that there is no perfect optimizer. You will always have to choose between performance, stability, and precision. So the fastest optimizer might be stuck in a different local minima each time. So And the first iteration, it can be stuck here, and the second be stuck here, etc., etc. So because there is some drawback and some advantages in DIPY, we decide to pick a preconditional gradient descent. So here you can see a table of all the advantages and drawback of all optimization method. You can see that the steepest descent is really, really unstable optimization method. This is why we didn't pick it. At the opposite of the PD and spiral, where it's numerically really stable, but have a really poor conversion speed. So as I said before, in DIPY, we decided to go to the BFGS method because he has the best trade-off between all of it. So the speed is correct, the stability is good, and the performance are respectable. So now I will show you how to use it with a DIPY. So in DIPY, we have two different ways to use the image, the affine registration. The first one is by using the DIPY command line as Javier presents you in the day one. To call this command line, you just need to do DIPY align affine your reference image and your moving image. So you can see here in the help of the command line that you have access to all what we described before, like the transformation. You can choose if you want just a translation, a rigid body, or an affine. You can also choose your sampling metric, meaning that you can tell us if you want 100% of your data or just a small percentage of it. You can also choose your metrics. Here, by default, we choose the mutual information because we assume that you are working with multimodal data. You can see that you can choose also the level of iteration for our image pyramid and the sigma to define how much smooth you want at each level of your pyramid. So defining these 2 points are really important and will improve the quality and the speed of your registration. Also, after using the command line, you can use code directly in Python. So there is a nice example in this link where we go in details on how to apply to do an affine registration. So you can see here that you can easily first set up a metric. Here we set up a mutual information matrix. Here you can see a list of different transformation. So we have the translation transformation 2D, the rigid transform, affine transform, and so on. You can go to DIPY align transform, and you can see that we have easily 10 or more different transformation. After defining your transformation and your metric, you just need to call the affine registration class where you define all the different components of your image registration algorithm. And then you just need to call the optimizer, and the optimizer will return you the new parameter, the new set of parameters that you need to apply on your moving image. So this is what we are currently using to do a motion correction. So to do a simple motion correction in fMRI, a rigid registration is completely enough. You will see that if you apply a rigid registration on your data, the motion correction will be really, really well done. Unfortunately, for doing an eddy correction, you will need an extra step because the eddy current correction are the eddy current are circular electric current induced within conductor by changing the magnetic field in the conductor. These imply that we have a change of intensity and we need a first step to regularize this intensity of the image to make sure that we register not only the movement of the data, but also the wrong intensity. We have a script who does that named motion-correct.py, and we will be happy to share it if you request it through the DIPY workshop chat. So that's all for the overview of the affine registration. I hope you enjoy this talk. I will see you on the talk, on the part 3 of this talk, talking about differomorphic registration. Thank you and bye-bye.